All right, in this unit, we're going to learn about some really important things for this class. And we're going to start off with something known as a mole. This is not the four-legged furry creature you might be thinking about. This is something else. A mole is like a dozen in that it represents a certain number of things. So for a dozen means 12. It doesn't matter what those things are. It could be donuts, could be chairs, could be people, could be books. A dozen, whatever, that would be 12 of those things. Likewise, a mole represents a certain number of things. Doesn't really matter what those things are. We'll talk in a little bit about what things this number applies to. So let me give you this number. You can jot this down. So a mole is that many things. So it's 602 and then 7 sets of zeros. We're going to use this number all the time. This is known as Avogadro's number. I'll write that spelling in just a minute. But we're not going to ever use it this way. That is just way too long to write it. So go ahead, pause the video, condense that into a more usable form. So hopefully you put that in scientific notation. Again, it's important to be able to use scientific notation on your calculator as we'll be using this number quite often. So again, this is known as Avogadro's number. 1 mole is 6.02 times 10 to the 23rd particles. Now, you may not notice, but this, or maybe you do notice, this number is really, really, really big. So let me give you some context. Let me give you some examples of how big this number is. 1 mole, so 6.02 times 10 to the 23rd grains of rice. How much area do you think that would take up? If you had a mole of grains of rice. Well, 6.02 times 10 to the 23rd grains of rice would cover the entire surface of the earth, the whole thing, to a depth of 75 meters. The fastest supercomputers today can count at a rate of about 1 trillion counts per second. And I got these examples a few years ago. It's probably higher than that, but we'll just use that number. It says even at that rate, it would take the computer 190,000 years to count up to 6 times 10 to the 23rd. Here's another one. If 1 mole of pennies were divided up among Earth's population, so there's about 7 billion people on Earth, each person would receive $100 trillion. Even each person spending that money at a rate of $1 million per day would not cause the money to be spent for almost 3,000 years. It's a huge, huge number. Let's do one more example. What if you had a mole of water molecules, 6.02 times 10 to the 23rd water molecules? How much water would this be? All of the water in the pond at Tri-City Park? All of the water in the Colorado River? All of the water in the Pacific Ocean? All of the water on all of the earth? Not quite. Let me show you. If you had 6.02 times 10 to the 23rd water molecules, it would be this much. It's about 18 milliliters of water. You're expecting something much larger, I take it? Well, here's my point. Though this is a really, really, really big number, the things that we're dealing with, such as water molecules, are really, really, really small. So a mole of something is really not that much. All right, this next section again is very important. It says a mole of particles. And so here's what we use Avogadro's number for. So these are the things that I referred to earlier in the notes. Particles could be formula units. So I know your notes don't say that, they say ionic compounds. We're going to add some stuff to your notes here. Formula units are the particles of an ionic compound. Or particles could mean molecules. Molecules are the particles of a molecular compound. Or particles could refer to atoms. Atoms are the particles of an element. Sometimes we can also use particles, or we can use ions as particles, but it's primarily these three things. Formula units, if what you're dealing with is an ionic compound. Molecules, if what you're dealing with is a molecular compound. And atoms, if what you're dealing with is an element. So let me start over. It says a mole of particles has a mass in grams which is numerically equal to the atomic mass, molecular mass, or formula mass of the corresponding element or compound. Let me give you some examples here. I have a block of aluminum. This piece of aluminum, here, let's make it bigger so you can see. This piece of aluminum contains 6.02 times 10 to the 23rd aluminum atoms. I should know, I counted every single one of them. Obviously, that's a joke. So this does contain exactly 6.02 times 10 to the 23rd aluminum atoms. Now, if I put this on a balance, what would the balance read? Go ahead and pause the video and see if you can come up with a number for me. The balance would read about 27 grams. Here is a piece of copper. This copper metal contains 6.02 times 10 to the 23rd copper atoms. If I put this on a balance, what would the balance read? Go ahead and pause the video. The balance would read about 63.5 grams. Here's a block of zinc. Again, this block of zinc contains 1 mole of zinc atoms, 6.02 times 10 to the 23rd zinc atoms. If I put this on a balance, what would the balance read? It would be a little more than 65 grams. Here is a piece of iron. This block of iron contains exactly 1 mole of iron atoms. If I put this on a balance, what would the balance read? It would be just under 56 grams. Here is a mole of sulfur. So sulfur is a nonmetal, it's a solid. It's a yellow solid, you can see there. Inside this is a mole of sulfur atoms. If I dump this out onto a balance, what would the balance read? About 32 grams. Here is a mole of sucrose, C12H22O11. If I dump this onto a balance, the balance would read 342 grams. Get my point? So those numbers on the periodic table, we've called them so far atomic mass, which is the mass of one atom in AMUs. Goes by another name too. It's called molar mass. That's number 3 in your notes. Molar mass, which is by definition, this is really important too because we'll be calculating molar mass in several different ways throughout the year. Molar mass is the mass in grams of 1 mole of particles. Sometimes it's called gram atomic mass for elements, or gram molecular mass for molecular compounds, or gram formula mass for ionic compounds. So now look at the definition. Think about the units. What are the units for molar mass? I'll give you a hint. It's not grams. Grams is a unit of mass. Look at the definition. We want molar mass. Go ahead and pause the video. See if you can come up with the units. So the units for molar mass are grams per mole. How do you like that there? My favorite abbreviation in all of chemistry, mole. So don't abbreviate with an M. That M means something else. So you can abbreviate it as MOL. Take off one whole letter. There you go. There's the abbreviation for mole. So grams per mole is how we read that. We can write it on a single line the second way I've shown, grams times moles to the -1, which is, again, grams per mole. So very important. So again, numbers on the periodic table. Not only are they atomic masses in AMUs, they are molar masses in grams per mole. All right, let's take a look at an example. We're going to make a table here at the bottom of the page. Let's start off with iron. Now it says atomic, molecular, or formula mass. So in the case of iron, it is an element. So go ahead and go to the periodic table, find the atomic mass of iron. Pause the video if you need to. So one iron atom has a mass of 55.8 AMU. What is the molar mass of iron? What is the mass in grams of not one iron atom, but 1 mole, 6.02 times 10 to the 23rd iron atoms? Go ahead and pause the video and write that number underneath molar mass. The molar mass of iron is 55.8 grams per mole. Let's try another substance. Sodium chloride is an ionic compound, so we're going to call it formula mass. So take a look at the periodic table, use your calculator, and determine the formula mass, the mass of one formula unit of sodium chloride. Go ahead and pause the video. Formula mass of sodium chloride, 58.4 AMU. Next up, go ahead and calculate or determine the molar mass of sodium chloride, the mass in grams of 1 mole of NaCl formula units. Pause the video. Maybe you're seeing a trend already. All right, let's keep going. Water is a molecular compound, so go ahead and calculate the molecular mass of water. Pause the video. So one water molecule has a mass of 18.0 AMU. How about a mole of water molecules? So calculate the molar mass. Pause the video. So there you have it. Again, we can do some more practice, but I think that'll be good enough for now. Again, the point I'm trying to make is the numbers on the periodic table are atomic masses in AMUs. They're also molar masses in grams per mole. We can calculate the molar mass of a compound the exact same way that we calculate formula or molecular mass. Same number, the only difference is the units. One of those particles, AMUs, a whole mole of them, that's going to be in grams. One of the most important skills in chemistry is something known as dimensional analysis or unit analysis, or as it's called here, the factor label method. We'll be doing a lot of converting from one unit of measure to another, and we're going to use something called a conversion factor. So these conversion factors are just a fraction, and this fraction is equal to 1. Now, I want you to think about this, and pause the video if you need to. What does a fraction equal to 1 look like? What does that mean? Go ahead and pause the video and be prepared to work with me on this. True or false, a fraction that is equal to 1 will always have the same number on top as on the bottom. So same number in the numerator as denominator. True or false? That is false. It's not always that way. So what does a fraction that is equal to 1 look like? The numerator and denominator must have the same, not number necessarily, the same quantity. If the quantity in the numerator is the same as the quantity in the denominator, then that fraction is equal to 1. So when we use conversion factors, we're not changing the amount, we're just changing the units. So we're going to start off with a pretty simple example using eggs. And I got to give you a couple relationships here so we can use these as our conversion factors. First of all, 1 dozen equals 12 eggs, so that'll be one relationship we'll use. And then 1 egg is 40 grams. And we're not going to worry about significant figures with these calculations. All right, first one. How many eggs would you have if you had 3.5 dozens? Now, I know what some of you are doing. You're going straight to your calculator and just going to give me that answer. No, there's a purpose behind this. I want you to set this up. We're not going to be doing conversions with eggs, but I want you to get used to this process. It's the process that we're looking for here. So let me walk you through it because there's a certain way that I want this done. Always start with the quantity given to you. So we're going to write 3.5 dozens. And then what are we trying to find? What does the question ask for? So we're given dozens, and we're asked to find eggs. Question, can we convert directly from dozens to eggs? Well, it looks like it. So let's do this. Next to 3.5 dozens, let's draw a conversion factor. When I say draw a conversion factor, all that means is we're going to take this 3.5 dozens and we're going to multiply by a fraction. And so I'm going to put that fraction in parentheses. So all we're doing here is we're multiplying fractions. All right, here's how it works. The units that we need to get rid of need to go on the bottom, because when we multiply these fractions, we want that to cancel. So in this case, we want dozens to cancel, so dozens is going to go on the bottom. Please, 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 no numbers. Put in the units first, and then we'll put in the numbers. All right, what are we trying to find? We're trying to find eggs, so the unit you want to convert to, that goes on top. Next, what is the relationship between eggs and dozens? All right, there are 12 eggs per 1 dozen. So again, remember that 3.5 dozens is really a fraction too. I'm going to write it this one time as a fraction. Never again after this, but I just want to prove to you that it is a fraction. All right, so what happens when we multiply these fractions? I don't care about the number yet. Let's take a look at the units. When you multiply 3.5 dozens by 12 eggs over 1 dozen, what happens? The dozens cancel, and that's good. What are we left with? Well, we're left with eggs. Is that what we were trying to find? Well, look at the question. It says, how many eggs? So we know we're good. Now we do the math. So we're going to take 3.5 times 12 eggs, and what do you get? You get 42 eggs. And again, I'm not really concerned about the answer. It's the setup that's more important. All right, let's take a look at another example. How many grams this time would 20 eggs weigh? Don't you dare touch your calculators. Don't even go there. I know how this works. So follow the process. Let's start off with a quantity given to us, which is 20 eggs. We're asked to find grams. Question is, can we convert directly from eggs to grams? It looks like we have this relationship here, so that means we can convert directly. So that means this calculation will require 1 conversion factor, since we can go directly from eggs to grams. So go ahead and draw your conversion factor. Units. Let's start off with eggs. Where must eggs go so that it cancels? We're looking for grams. Where must grams go so that it doesn't cancel? So that's the unit that we end up with. And then the numbers. What is the relationship between grams and eggs? Remember, we need the same quantity in the numerator as the denominator. 1 egg is equal to 40 grams. Let's multiply. Start off with the units. Looks like eggs cancel. And then we do the math. And again, I will care later about sig figs. Here, I don't care about sig figs. I just want to focus on the process. All right, you give it a try. Number 3, how many eggs would you have if you had 600 grams of eggs? Go ahead and pause the video, set it up, and get your answer. Pause now, please. Here's the setup. Hopefully you got something just like that. And again, I don't really care about the answer. The setup is way more important than your final answer. Let's take a look at some more. How many grams of eggs would you have if you had 8 dozen? So again, we're going to start the same way. Start off with the quantity given to us. And we're looking for grams. Question is, can we convert directly from dozens to grams? Take a look at the two relationships towards the top of the page. There's nothing that allows us to go directly from dozens to grams. So this calculation will require more than one conversion factor. Well, how are we going to do this? How about this? What do dozens and grams have in common? Well, they have eggs in common. So maybe we can go to eggs first and then to grams. Let's do that. Now, I don't want to do two separate calculations. I know some of you are probably working ahead of me, which is a mistake. Work with me. So this calculation is going to require two conversion factors, and I'm going to set them up all together. We're going to do this all in one shot. Remember, all we're doing is multiplying fractions, so we can just do this all together. Let's go one conversion factor at a time. So let's start with dozen. We need dozens to cancel, so where must that go in our first conversion factor? Now remember, we need to go to eggs first before we can go to grams. So let's convert from dozens to eggs. So let's put eggs on top. Again, please, units first and then numbers. So what is the relationship between eggs and dozens? And cancel your units as you go. So after one conversion factor, dozens cancel. Now we have eggs. Okay, second conversion factor. Where must eggs go so that it cancels? And we're trying to find grams, so where must grams go so that it does not cancel? What is the relationship between grams and eggs? When we multiply those units, eggs cancel, we're left with grams. Go ahead and pause the video and see what you get. So what is the relationship between 3,840 grams and 8 dozen? 8 dozen eggs and 3,840 grams of eggs. They're the exact same thing. We're not changing the quantity. We're just changing the units. All right, give number 5 a shot. Again, similar problem. We cannot go directly from grams to dozens. So this calculation will require two conversion factors. Go ahead and pause the video, set it up. So what'd you get for your answer? Well, it should be noted that in this class, we don't ever, or hardly ever, put answers to calculations as a fraction. So more often than not, we're going to express an answer to a calculation as a decimal. So if you wrote a fraction, get rid of that. So let's convert this to a decimal. And again, it should show up right on your calculator. And we'll just write 3 sig figs, even though that's not the correct number of sig figs here. We'll go 3 sig figs. So what do we end up with? Now, does that answer make sense? Can you have 2/3 of a dozen? Sure, you can. Can you have 2/3 of an egg? That doesn't make sense. You can't have part of an egg, but you can have a fraction of a dozen. I'm going somewhere with this, of course. So make sure your answers make sense, though doesn't make sense to have a fraction of one thing, a fraction of an egg. We can have a fraction of a dozen. So obviously, we're not going to be using conversions involving eggs. We will be using conversions involving moles. And so we'll see that next time. So focus on this process. The process for doing mole conversions is very similar, almost the same as using eggs. All right, thanks for watching. See you next time.